Jai Hind. Myself Ravind Kumar from AP from EN Department, Ajay Kumar Garg Engineering College, Ghaziabad. Today I am presenting my topic transformer losses and efficiency, and this is covered under the subject Fundamentals of Electrical Engineering, for which subject code is BEE 101 for the first SEM, that is odd SEM, and BEE 201 for the even SEM. So the students who are taking this subject in even and odd SEM, accordingly this code will be there. So under this topic, I will be covering the various losses which are taking place in a transformer, and then the calculation of efficiency from that. Plus, we will also find how the maximum efficiency condition is found, and accordingly we can calculate maximum efficiency value also for a given transformer. So if we see in this, what are the different losses that we can see in the coming slides. Losses in a transformer, if we see it, the losses which are taking place in a transformer, mainly there are two types. One is iron loss. One is iron loss. It is also known as core loss. Reason being, core is made up of iron. That's why we call them iron loss or core loss. And second one is copper loss. We call it Cu loss, Cu for copper. So these are the basically two types of losses in a transformer which are taking place. There is no friction loss in a transformer. Reason being, transformer is a static device, so that there is no question of friction. Friction only takes place when some motion is there. So there is no friction in a transformer due to a static device, and no question of friction losses in a transformer. Now if we elaborate these losses, or if we discuss these losses, then we can see this first type, iron loss or core loss. This is the power loss that occurs in the iron part of the transformer, or we can say in the core of transformer, and this loss is due to the alternating frequency of the EMF. Iron loss can further be classified into two other losses. One is eddy current loss, second is hysteresis loss. So from this we can see one more thing, that this iron loss, since it is dependent upon frequency, so if DC supply is there is no question of iron loss, since the frequency of DC supply is 0. So first, if we discuss about eddy current loss, what is this? This is the power loss due to the alternating flux linking with the core of transformer, and due to this alternating flux, an EMF will be induced in the core of transformer, and that is known as eddy EMF. And due to this eddy EMF, a current is also induced, that is known as eddy current, and this eddy current is circulating in the core. There are circulating current paths through which this eddy current is circulating in the core. As there is some resistance in the path of eddy current that is offered by the core. So due to this eddy current losses will take place in form of heat, and those are known as eddy current losses, power loss. Eddy current loss, that is proportional to the square of supply frequency. So for minimizing the eddy current loss, what we do, we laminate the core. Why do we laminate the core? That we will discuss in the next slide, how we reduce or minimize the eddy current loss by laminating the core. So if we see here, mathematically, eddy current losses, they are expressed by P, that is representing eddy current power loss. This is given by K into B max square into F square into T square into V. The symbols are P, that represents eddy current power loss in watts, K is eddy current constant, B is the flux density in Weber per meter square. So B max we are writing here, that is maximum value of flux density. F is the frequency of AC supply, that is we also say magnetic frequency of magnetic reversals per second in hertz, and T is the thickness of the core material that we are using, and V is the volume of the core in meter cube. So this is the expression for calculation of eddy current power loss. And from this we can see the eddy current power loss, they are dependent upon square of the frequency of supply plus square of the thickness of the core also. So if we reduce the thickness, accordingly eddy current power losses are also reduced. So from this we can see here, it is a laminated core in which we are using thin strips. A number of strips they are taken, thin strips, and varnish coating is put over those strips, and then all those strips are assembled so that the formation of core takes place for the transformer. And by doing so, when we are able to reduce the thickness by using the thin strips, eddy current losses are also reduced as a result of that. In place of that, if we take solid core, then this will be the path of circulating current, and since the thickness is more here, so that eddy current losses will also increase accordingly if it is a solid core rather than laminated core. So that's why laminated core is used for reducing or minimizing the eddy current losses. These are the path of eddy currents. All these are path of eddy currents, and that is getting reduced by lamination of core. These are laminations, thin strips. These are all known as laminations, which are taken by help of thin strips. The thickness of the strip that can be taken 2 mm or 3 mm in that range, so that we can laminate the core properly. Next we have hysteresis losses, that is also the part of core loss or iron loss. This is the loss in the iron core due to the magnetic reversal of the flux in the core, and that results in the form of heat in the core, and this is known as hysteresis power loss. This loss is directly proportional to the frequency, supply frequency. Eddy current losses can be minimized by using the core made up of thin sheets of silicon steel material, and each lamination is coated with varnish insulation to suppress the path of eddy currents. Hysteresis losses can be minimized by using the core material having high permeability. By doing so, that means by using the core material of high permeability, the area of BH loop that becomes minimum, and with minimum area, hysteresis losses are also minimized. Since hysteresis losses in the core, they are directly proportional to the area of the BH loop. So by this using high permeability core material, hysteresis losses are minimized with the help of it. Further, if we see the hysteresis losses expression, this is hysteresis loss, that is represented by pH. This is pH, hysteresis loss, and that is equal to eta into B max raised to the power n into F into V. The symbols are pH represents hysteresis loss in watts, eta that is hysteresis coefficient depending upon the material, and B max is the maximum value of flux density in Weber per meter square, n that is Stevens exponent or Stevens constant. It range for n is from 1.5 to 2.5 depending upon core material, and F is the frequency of AC supply, that is the frequency of magnetic reversals per second in hertz, and V is the volume of magnetic material in meter cube. So again the conclusion drawn from here, if the DC supply is taken, frequency 0 in DC, so hysteresis losses will not occur in case of DC supply, and with the increase in frequency, hysteresis losses will increase. And basically this is the BH loop. There are different terms in this: saturation, retentivity. Corresponding to this, we have residual magnetism from this point to this point, that is residual magnetism, and the property of core corresponding to this, that we call retentivity. This is corrosivity from this point to this point, and corresponding to it we have corrosive force. This is saturation in opposite direction. So overall, if we see the area of this BH loop or magnetizing loop, that is directly proportional to hysteresis losses. So if we have a smaller area of this loop, hysteresis losses will also be small in the core. So that's why we take high permeability core material, so as to reduce hysteresis losses in the core. Next we have copper losses. This is the power loss which occurs in the primary and secondary winding or coil of the transformer when it is connected with some load impedance. Secondary side of the transformer is connected with some load impedance. See, that time current is there on both the sides, primary as well as secondary side. This power is wasted in the form of heat due to the resistance of coil. This loss is proportional to square of the current, that is load, since load means current or power. Hence it is called variable loss, since with the variation in load current corresponding to square of that current, this loss will also vary. That's why we call it variable loss. While iron losses, they are constant losses since they are independent of current. They depend upon supply voltage and frequency, and if we keep supply voltage and frequency constant, then core losses will remain constant, but load can be varied even after keeping supply voltage and frequency constant, so that with the variation in load, that means variation in current and power, the copper losses will get vary, since copper losses are dependent upon square of the load or square of the load current. That means, so copper losses, they are written as I square R losses. So when we take both the windings in consideration, so this is I1 square R1 plus I2 square R2, where I1 is primary side current of the transformer, R1 is primary winding resistance, I2 is secondary current of the transformer, R2 is secondary winding resistance of transformer. So these are the symbols I1, I2, R1, R2. Now if we talk further about efficiency of a transformer, so efficiency that we know, this is the ratio of output power to input power for any machine or any transformer. Input power can be written as output power plus losses which are taking place in the transformer. And already we have discussed the losses which are copper loss and core loss. And core loss includes hysteresis loss and eddy current loss. So efficiency can be written as, this is the symbol for efficiency, this eta, that is output power upon input power, and input power can be written as output power plus iron loss or core loss plus copper loss. Now output power that is obtained in the secondary of transformer, since the load impedance that is connected across secondary winding terminals, so output power is obtained in the load impedance, so that's why it is obtained from secondary side, and that can be written as V2 I2 cos phi 2, where V2 is load voltage, I2 is load current, and cos phi 2 is power factor of the load which is connected across secondary terminals of the transformer, upon V2 I2 cos phi 2, that is output power again, plus iron losses W iron plus copper losses W copper. So that way we can calculate the efficiency of a transformer. V2 is secondary output voltage across load, and I2 is secondary output current, and cos phi 2 is power factor of the load. So from this we can also derive the condition of maximum efficiency of a transformer, plus we can calculate efficiency of a transformer with the help of it. Normally the power rating of a transformer that is given in kVA, reason being the losses which are taking place in transformer like copper loss and iron loss, they are independent of power factor. Copper losses, they depend upon square of the current, while iron losses or core losses, they depend upon square of the voltage. And since both the losses, they are independent from power factor, that's why output power that can be taken as the product of voltage and current only, since that is independent from power factor. That's why the power rating of a transformer can be taken as in volt ampere or kilovolt ampere or megavolt ampere. So efficiency can be written mathematically as kVA, output power rating or rated power of the transformer, multiplied by 10 raised to power 3, so that we can convert this power to VA, volt ampere, multiplied by power factor, so that this power comes in watts, divided by output power again, kVA into 10 raised to power 3 into cos phi, plus iron losses, that is W iron, or core losses we can say it, plus copper losses, W copper. Now copper losses, they are variable losses that already I have discussed. They depend upon square of the load or square of the load current. While iron losses or coal losses, they are constant losses. So basically in this expression of efficiency, load current, that is independent variable, and efficiency dependent upon load current of the transformer. So efficiency can be written at any desired load which is n times of full load power rating of the transformer. That efficiency can be written as n into kVA, rated kVA, that means into 10 raised to power 3 into cos phi, power factor of the load, divided by n into kVA into 10 raised to power 3 into cos phi, plus iron losses plus n square into copper losses. Why we are taking n square with copper losses in multiplication? Since copper losses are dependent upon square of the current, and when we are taking n times of full load current, that time copper losses will become n times of full load current square into resistance. So this becomes n square times of full load copper losses. This is W copper represents full load copper losses. FL means full load. So this W copper is copper losses at full load, and W copper can be written as I square R or IFL square into R, where IFL represents full load current corresponding to full load condition of the transformer, and R is the resistance of the winding. So again, if we find the condition for maximum efficiency of a transformer, what can we do for this? For maximum efficiency of a transformer, already we have seen efficiency of the transformer, that is given by this expression V2I2 cos phi 2 upon V2I2 cos phi 2 plus iron or coal losses plus copper losses, that can be written I2 square into RE2. RE2 is equivalent resistance in secondary side and I2 is the current in secondary side. So total copper losses can be given by this expression I2 square RE2. It will include copper losses of both the sides, primary as well as secondary. Now by dividing the expression of efficiency with I2, we will get V2 cos phi 2 in numerator, and in denominator we will get V2 cos phi 2 plus Pi upon I2 plus I2 into RE2 after division from I2 in the expression of efficiency. Now the value of terminal voltage V2, that approximately remains constant. So for a given power factor, the efficiency of transformer, that is basically dependent upon current, load current I2. And in this equation of efficiency, equation number 1, we can see numerator becomes constant since V2 is constant, that also almost constant value, and cos phi 2 given power factor, that is also constant. So as a result, numerator is constant, but denominator is not constant since current I2 is there in denominator. So transformer efficiency will be maximum if denominator becomes minimum. And for that, what we do, we differentiate denominator with respect to variable current I2, load current I2 in the secondary, and equate it to 0 so that we can get the condition for maximum efficiency. So what we have done here, we differentiated the denominator, that is this V2 cos phi 2 plus P upon I2 plus I2 into RE2 with respect to current I2. We have differentiated it and then equated it to 0 so as to get the condition for maximum efficiency. So after differentiation, we will get 0 minus Pi upon I2 square plus RE2, that is equal to 0. And from this, we get I2 square into RE2 equal to Pi, where I2 square into RE2, that represents copper losses which are taking place in transformer, and Pi is coal loss or iron loss in the transformer. So as a result, we get that copper losses should be equal to iron losses for maximum efficiency condition of a transformer. Or we can also say variable losses equal to constant losses for maximum efficiency of a transformer. Reason being, copper losses are variable losses and iron losses are constant losses. So we can also call it that variable losses should be equal to constant losses, so that we can get maximum efficiency of a transformer. That way we can get maximum efficiency condition of a transformer. Further, the value for maximum efficiency that can also be calculated, eta max, that is maximum efficiency. It will be V2I2 cos phi 2, which is output power, upon V2I2 cos phi 2 plus 2 into Pi. That means double of iron losses or core losses. Reason being, already we have discussed that for maximum efficiency, copper losses equal to core losses. So, for maximum efficiency condition, we put copper losses equal to core losses. That's why we can also write double of core losses or iron losses. Since iron losses remain constant throughout, whatever variation in the load is made, but iron losses remain constant. And from this equation, we get the value of output current I2, for which we will get maximum efficiency of transformer. That current I2 will be given by under root of Pi upon Re2, where Pi is core losses or iron losses in the transformer, and Re2 is equivalent resistance in secondary side of transformer. Now, if X is the fraction of full load kVA at which the maximum efficiency can take place in the transformer, then copper losses will become X squared times of copper losses at full load. So, PC is full load copper losses, and iron losses are constant, that already we have seen. That's why iron losses are Pi or core losses we can call them. Now, for maximum efficiency condition, copper losses should be equal to core losses. So, X square into full load copper losses should be equal to core loss or iron loss, so that maximum efficiency can be achieved. And from this, X becomes under root of Pi upon PC, where Pi, that is iron losses or core losses, and PC, that is basically full load copper loss. We can also write it PCUFL, full load copper loss. So, this is under root of Pi upon PCUFL, that is equal to X, which is the factor in product with full load. That means the load X times of full load at which maximum efficiency can take place. So, the load in kVA corresponding to maximum efficiency of a transformer can be written as X times of under root of iron loss upon full load copper loss, and full load kVA, that will be written, since we are taking X times of full load and the value of X is under root of iron loss upon full load copper loss. So, by putting that value of X here, this is X basically, this factor is X, that already we have found, that is S. So, multiplying this X with full load kVA, that becomes the kVA load corresponding to which we will get maximum efficiency of the transformer. Now, some numerical examples related to it. Some numerical examples related to it. A 200 kVA rated transformer has full load copper loss of 1.5 kilowatt and iron loss of 1 kilowatt. So, we are to find the efficiency of transformer at full load and 0.85 power factor, and at half of full load and 0.85 power factor. So, full load output power, that is V2I2 cos phi 2, that becomes 200 into 0.85, that is 170 kilowatt. Since 200 kVA multiplied by power factor, that becomes 170 kilowatt. Total losses, that are copper loss and iron loss, that becomes 1 plus 1.5, that is 2.5 kilowatt as per the data given to us. Input power, that is output power plus total losses, so that becomes 170 kilowatt output power plus 2.5 kilowatt total losses. So, this becomes 172.5 kilowatt. Now, the efficiency is 1 minus losses upon input power. So, by putting the value of losses and input power in this, efficiency comes out as 98.55% at full load. Next, for half load condition, the efficiency calculation. At half load, the output power becomes half of full load power. So, that is 1 by 2 or 0.5 times of 200 into 0.85 power factor. So, this becomes 85 kilowatt. Copper losses, they are proportional to square of current. So copper losses at half of full load becomes 1 by 4 times or 0.5 square times of full load copper loss, that is 1500 watt. So this becomes 375 watt. Iron losses are constant, so they remain 1000 watt since they are constant. So total losses becomes 1000 plus 375, that is 1375 watt. Input power is output power plus losses, that is 85,000 watt plus 1375 watt. So this is 86,375 watt. So efficiency at half of full load becomes output power, that is 85,000 upon input power, that is 85,000 plus 1000 plus 0.5 square into 1500. So and in percentage, if you want to find it, multiply it by 100. So this becomes 98.41%. So that way we can calculate the efficiency of transformer at half of full load. One more example we can have in this. What we have, a 500 kVA transformer has 2500 watts iron lossage, 7500 watts copper lossage at full load. Power factor is 0.8 lagging for different load conditions. We are to find transformer efficiency at full load, maximum efficiency of the transformer, output kVA corresponding to maximum efficiency, and transformer efficiency at half load. So this value of power which is given and nothing is written with that, that is represents rated power of the transformer or full load power of the transformer, which is 500 kVA as per this. So multiplying it by power factor, we get power in watts, that becomes 4 lakh watts, and iron losses are 2500 watt, that is given, they remain constant, they are independent from load. Full load copper losses are given 7500 watt. So efficiency of transformer at full load becomes this output power upon output power plus lossage. In this, we are taking full load copper loss since we are operating the transformer at full load for calculation of efficiency at full load. So this comes out as 97.56%. Now next we are to find maximum efficiency of the transformer and the kVA load for which maximum efficiency test can take place. So for this, as we already have seen, that kVA load for which maximum efficiency takes place, that is given by full load kVA into under root of core loss upon full load copper loss. So full load kVA is 500 as per the question given to us into under root of 2500 upon 7500. Since 2500 that represents iron losses or core losses in watts and 7500 is full load copper lossage. So this comes out at 288.675 kVA. That means corresponding to this load, we will get maximum efficiency of the transformer when transformer is operated at this kVA, that is 288.675 kVA. So for maximum efficiency, also we have seen that copper losses should be equal to iron losses, and iron losses are constant. So copper losses will become equal to iron losses, that is 2500 watt, and maximum efficiency becomes this output power that we have found for maximum efficiency into power factor divided by output power plus double of iron losses, since copper losses and iron losses are equal for maximum efficiency. So this comes out as 97.88%. Now last part, transformer efficiency at half of full load. This is half of full load. So this is 0.5, that is half of full load, divided by input power half of full load plus iron losses that are constant 2500 watt plus copper losses at half of full load. So this is 0.5 square into 7500, where 7500 is full load copper loss. It is multiplied by 0.5 square since load becomes half, and copper losses, they are proportional to square of the load current. So when load current becomes half due to half load, so copper losses becomes square of 0.5. Proportional to square of 0.5 or proportional to square of 1 by 2. So on calculation, we get the efficiency value as 97.86% at half of full load for this transformer given to us as per the data. So we have found the different cases. Half of full load efficiency is this 97.86%, maximum efficiency 97.88%, and full load efficiency was 97.56%. So that way we can calculate losses in the transformer and efficiency of the transformer. Main thing which is important in this, core losses or iron losses remain constant with the variation in load, while copper losses, they depend upon load and they are proportional to square of the load current. So with the variation in load current corresponding to square of load current, proportional to that, copper losses are varied and they can be calculated. But output power, that is proportional to load current. So with the variation in load current, proportional to that, output power also varies. And with the help of all these concepts, we can calculate the efficiency of a transformer corresponding to various load conditions. Plus, we can also calculate the kVA load for which maximum efficiency can take place in a transformer, and we can also calculate the value of maximum efficiency of a transformer. And one more important point in this, if we operate a transformer without any load or on no load condition, efficiency becomes zero. Since no load means no current, no power, so that output power becomes zero, copper losses becomes zero due to no current, but core losses remain constant and efficiency output power upon input power. When output power becomes zero due to no load, that means no current, no power, so the efficiency of the transformer becomes zero at no load condition. So that's all about this. In the next lecture class, I will be discussing another topic related to transformer. Jai Hind.